Welcome all. Good afternoon. As the scientific coordinator of the Center for Philosophy of Science of the University of Lisbon, I'm delighted to open this session of our permanent seminar, this time again on hybrid formats. So it's still this new kind of thing. Today's speaker will be Professor Maurício Suarez. Professor Maurício Suarez is a professor in logic and philosophy of science at the Complutense University of Madrid. He previously taught at Oxford, St. Andrews, Northwestern, and the Bristol universities. He has held visiting appointments at Sydney, Harvard, London, Paris 1, Sorbonne, Vienna, and Vienna universities. He has published over more than 100 papers in his specialty, edited or co-edited 4 books for Routledge and Springer, and his latest authored book is entitled Inference and Representation, forthcoming on the University of Chicago Press. So the title today will be The Possibilities in Propensities. And I just want to thank Professor Maurício Suarez for accepting our invitation. We are very glad that you are here finally. And it's a great pleasure and an honor to have you in our permanent seminar. So
good. So I wanted to say thanks very much. Muito obrigado for the invitation, which has been long coming. The last few years have been very difficult for everybody, and traveling has not been easy. So this is a sort of much delayed visit. I'm glad that it finally happened. And also very glad that everybody who is turning up for this talk at the very end of the summer, it must be really hard for everyone to be here. So I appreciate the effort. This talk is actually a continuation of a talk that I gave on Zoom. I think it was last November, so it's coming up to a year for a teaching course on philosophy and statistics. And so part of what I will do here at the beginning of the talk is to summarize what I already said last year, both for those of you who were here, to just remind you of what it is that we talked about then, and for those of you who weren't here in November, so that you know roughly what the framework, the philosophical framework for this whole project is, because I will get quite specific later on, and it gets a little technical at the end, but I hope that the beginning of the talk is accessible to everybody. Also, I wanted to begin the talk by remembering the figure of Paul Humphreys. You may have heard that he died young and suddenly just a couple of weeks ago. And it touches me quite a bit, the death of Paul Humphreys, because a lot of what I'm doing in the philosophy of probability has a direct link to things that I learned from him 15 years or so ago. There is something in the field, in the philosophy of probability, called Humphreys paradox. And this has been a cornerstone of a lot of my work, and it has driven a lot of my work in the philosophy of probability. And in some ways, I sort of saw myself as sort of filling in the details of some of the issues and some of the philosophical approaches that Paul Humphreys had defended in the past. So I was really sad when I heard the news. And this is a bit of a talk in his honor as a result of his death. Okay, so the work that I'm going to talk about is long-rooted and is part of a project that has been ongoing for a good 15 years now. As I mentioned, I was reading these papers by Paul Humphreys and books by Donald Gillies and other experts in the philosophy of probability about 15 years ago. And then I was doing this in the context of some work in the philosophy of physics. And I came up with a new propensity account of quantum mechanics. You may have heard that the propensity interpretation of quantum mechanics is one of the things that made Karl Popper famous. And you must have heard of Karl Popper. You all know who Karl Popper is. So Karl Popper was made famous, or maybe I should say he was made infamous, by this propensity interpretation that everybody agrees is wrong. Everybody agrees this propensity interpretation of quantum mechanics D2 Popper is wrong. So when I started working on this 15 years ago, propensity accounts of quantum mechanics were like no-go areas. You don't go there. That's not something you want to do. And it occurred to me that the problem with Popper's account was not so much the idea of propensity, but the way in which he understood propensities, his particular interpretation. The Popperian interpretation of propensities was the problem, not the idea of propensity in itself. So I came up with an alternative understanding of propensities, very much influenced by Paul Humphrey's work. And then I applied it to quantum mechanics, and lo and behold, I solved the measurement problem of quantum mechanics by doing this. Not that I have convinced many people that this is a solution to the measurement problem, but I'm still convinced 15 years later that it does solve it. And then I deepened my understanding of propensities, and I came up with something that I call the tripartite conception of objective probability. And that's already in the very long introduction to this volume that I edited in 2011. If you want to look at the origin of these ideas, it's all in that introduction, in the context of the philosophy of physics. Then that kind of got developed later on. I spent a couple of years in London working on a Marie Curie fellowship, and I had a chance to expand this interpretation of probability in physics to other areas of science. And I came up with a new formal account of the relationship between propensities and probabilities. I'll tell you a little bit about that in a minute. That's all in a BJPS paper that came out in 2016. And then eventually that culminated in this book that I published in 2020 for Cambridge, the Elements collection, the Element series on the philosophy of probability and statistical modeling. And that's my most up-to-date thinking on the topic, and basically what I talked about last year on the teaching course. Today, what I want to do is just remind you of what I said last year, what's in that 2020 book for Cambridge. And then I want to push on a little bit. And I want to start talking about things that are not in the book and that concern modality, and in particular, the modality of possibility. So this is going to be an attempt to get a formal grip on some very philosophical notions that emerge from this technical work in the philosophy of science. Let me tell you, the first three sections will be known to those of you who were here last year. First, I present a very broad framework that I defended last year. I call it Pluralism about Objective Probability or Chance. Then I give you the formal description of probabilities and propensities that is in the British Journal for the Philosophy of Science 2016 paper. I still very much defend that. That's something that Paul Humphreys liked very much, by the way. He comments on it in books that he published later on and so on. So that's the part where I feel I will be most remembering Paul. And then I talk a little bit about the statistical models, very simple statistical models. Rather, statistical models of phenomena that you may think is very simple. By tossing a coin, you would think nothing is simpler as a chance experiment than tossing a coin. You toss a coin, it might land heads or tails. It has a certain probability of landing heads, certain probability of landing tails, and you may think, oh, that's really easy. That's very simple probability. Well, I want to suggest not as simple as it may seem. Producing a statistical model for that phenomenon is already quite difficult and involves three different levels of property ascriptions that I want to discuss here. And from that, I'll just come up to the tripartite conception of probability, my latest version of it. And I want to link that, this is the stuff that is new, to conceptions of possibility that are discussed in the philosophical literature, in analytical metaphysics and elsewhere. And I'll very quickly review two examples where you see how this all works, because I claim this is not just idle metaphysics. This is really productive philosophy of science that can help solve problems in the foundations of some scientific disciplines. Yes, I do claim that. Of course, I'm sure that we'll want to discuss whether that's the case or not. So very quickly, what I've been defending since 2000, whatever, a very long time ago, is a sort of pluralism about objective chance that's already in the tradition of some very established, I think everybody accepts pluralism about probability in general. This comes from Ramsey. This was defended by Ian Hacking. This is actually in Rudolf Carnap, who distinguished probability sub 1, probability sub 2. Many authors have drawn this distinction. Most philosophers of probability believe that you need this distinction. Not everybody, but most philosophers of probability think you have to distinguish subjective probabilities that are in the head from objective probabilities that are out there in the world. And probability refers to both ideas and to both concepts. And somehow, amazingly, the same calculus, the same mathematical calculus helps us to understand both. But they are distinct. One is a matter of credences or mental states in the mind, and therefore it's a matter of information and partial degrees of belief. The other one is about phenomena that happens in the world and how frequently it happens, what kind of frequency it exhibits. So they're really two different things, and it's kind of an amazing coincidence that probability helps us to manage, handle, and describe both. This is, as I say, widely accepted by philosophers, widely accepted by statisticians. So what I'm doing is just arguing, if you accept pluralism about probability in general, why don't you go just one step a little beyond and accept it also for objective probability itself, or objective probability, chance. So I claim, and I've been defending for some time now, that when it comes to probability sub 2, Carnap's useful term, which is supposed to measure chance, it really is an ambiguous term referring to three different things, and we have to distinguish those three things. And that probability sub 2 refers usefully to all those three things. But in order to understand how it appears in the sciences and how the sciences represent chancy phenomena, you really need to be carefully distinguishing conceptually the three notions, namely theoretical propensities, what I call single case probabilities. I talked a lot about this last year. I'll do a very brief summary of that again today, and then frequency statistics, which is the numbers that you get when you run an experiment, the kind of observations that you get in an experiment. Now, and you may think, okay, theoretical propensities, they're just properties of objects or systems. Probabilities are the sort of probabilities that they exhibit, and frequencies are the numbers that you collect when you run the experiment. It seems trivial, no? Well, surprisingly, a lot of the philosophy of probability of the last century has devoted itself single-handedly and very firmly to rejecting that there are three different notions. So most of the philosophy of probability of the 20th century is one way or another an attempt to reduce all of these three notions to just one of them. So Popper's famous propensity interpretation is trying to reduce probability to propensity. Von Mises' famous frequency interpretation of probability, the logical empiricist interpretation of probability, attempts to reduce probability to frequencies and claims there's nothing else really to talk about. So these are all attempts to do away with one of the three notions that I think are indispensable. So this is the sense in which I defend pluralism. I'm an anti-reductionist about these notions. I think you need them all in order to understand properly how objective probability works in science. And I think it's a sad accident that a lot of 20th century philosophy of probability has devoted itself so single-mindedly, obsessively, to the project of reduction. Because if we learn anything from the philosophy of probabilities, that none of those reductive attempts work. And this is, in fact, what's wrong with Popper's interpretation of probability. The attempt to identify propensities and probabilities that leads him astray, and the reason why he can't solve the measurement problem and other problems in quantum mechanics. So my pluralism is part of a long tradition, but it's at the same time strangely revolutionary, because a lot of philosophers of probability have really attempted a very different project. And here I have to say I'm really indebted to people like Donald Gillies and Paul Humphreys. They were the first pluralists about objective probability. They're the ones who really started this project of separating this. And Humphreys' paradox is just an argument that tells you cannot identify propensities and probabilities. They're different things. That's the great gift that Paul Humphreys gave us, philosophers of probabilities, is to have understood that mistake that we were making. And I'm just pursuing this Humphreys idea further here. Here's the paradigmatic example. A coin has propensities. It has some certain physical features that explain its behavior. When you toss it, the coin exhibits a certain probability to fall heads or tails. If the coin is symmetrical and the center of gravity coincides with the center of geometrical center, and it has no thickness and a bunch of other assumptions about the coin, then you can ascribe 50-50 probability to heads and tails. But you need a bunch of assumptions. And I'll say some more about that in a second. And finally, you test that, the ascription of probability to the coin toss. Say if the coin is fair, you say the probability has 50% chance of falling heads or tails. You test that by tossing a coin repeatedly and looking at what happens. And if you get something like 51 heads and 49 tails in 100 tosses, then you have good grounds, maybe, that sounds like good evidence to claim that this coin may be fair. But if you get 99 heads and 1 tails, that's starting to look like really good evidence to think that this coin is biased, right? We all are aware of this distinction. So the coin has properties. When you toss it, the toss has a probability. And this is exhibited in frequency outcomes that you can experimentally measure. 3 different things: the properties of the coin, the probability that resides in the toss. The coin by itself has no probability. It's a coin being tossed that has a probability of falling heads or tails. And then finally, the results of your observations. 49-51 looks like good evidence the coin is fair. So we naturally make these distinctions, right? Why would anybody think that all these 3 can be collapsed into just one notion? I don't know. It's a very interesting historical question for the History of Philosophy of Science Association to answer. I have no real answers to this question, but I just want to claim this distinction is really familiar to all of us. It's very much on your face. Anybody who's run an experiment with coins is already familiar with this tripartite distinction. And I'm just saying, well, let's apply that to science. Okay, so this was the theory that I presented, and there is in the 2020 book. I claim, in response to Humphreys paradox and just following on Paul's pioneering work in this area, that propensities or probabilities dispositions are displayed in probabilities over events. This is unlike what happens in deterministic systems. The coin toss is an indeterministic system, as you will see in a second, even though the underlying dynamics is deterministic. There's a precise sense in which you can talk about indeterminism there. And the coin has certain probabilities that generates, the coin has certain properties that generate probabilities in its tossing that can then be checked by just looking at the statistics. So here the key term is, and this is a term that I introduced. I don't think Paul had quite introduced this term, although I'm sure that he had it in the back of his mind when he wrote the stuff on Humphreys paradox, that the propensities generate the probability functions that display those propensities. It's something in the constitution of the coin and in the chance setup, the whole setup in which you're tossing the coin, that gives rise to those probabilities. If the coin is different, if it's a bent coin, then the probabilities will be different. So the probabilities are somehow grounded, this is the terminology that I employ, on the propensities of the coin and maybe farther of the whole chance setup in which the coin is tossed. And I even came up with a notation. This double arrow just means it's the sui generis relation that propensities bear to the probabilities that display them. And as I said, this comes to some extent from Humphreys' work. Now, this is important because if the propensities generate the probabilities, then it would be wrong to say that the propensities can be within the probability spaces that are defined by those probability functions. And you all know this. A probability is a mathematical function that takes you from a sample space to the unit interval of the real numbers continuum, of the continuum of the real numbers. everybody is familiar with this idea, right? But here, the probability function has a sample space over which it is defined. But if the propensities generate the probability functions, then the propensities cannot lie within the probability space of those probabilities that they generate, by definition, because they're the generators of these probability functions and these spaces. And so this turns out to be important. It turns out that propensities do not live, do not exist within the sample spaces of the probability functions that they generate. And this is in essence what Paul Humphreys discovered. The Humphreys paradox is an argument that shows you that if you allow the propensities to be back into the probability spaces of the functions they generate, you get a contradiction with the Kolmogorov actions. That's what Paul showed formally. It's a theorem. He showed it as a theorem. And he then suggested maybe we should give up on Kolmogorov. Well, it was one possible suggestion. I suggest instead, don't give up on Kolmogorov, give up on the idea that the propensities live within the probability spaces of the functions that they generate. So that's my way of getting around Humphreys' paradox. And I talked a lot with Paul about this, and anyway, it was a back and forth. And we both understood what the problem is. We sort of differed a little bit in the way we went about answering it. This turns out to be important, and it's important for all the conceptual conundrums that I'm going to be addressing today by means of this tripartite conception of probability. If you accept the tripartite conception of probability, this is all in the Cambridge 2020 book, and I spoke about it last year, then the propensities cannot exist in the probability spaces, the outcome spaces of the probability functions that the propensities generate. So the fact that the coin is fair cannot be an outcome of the probability function that is generated when you toss the coin. The only outcomes are falling heads or falling tails, but not being fair and being unfair. Those are not attributes that figure in the outcome space and cannot figure in the outcome space, or having the propensity to be fair. That's not in the outcome space. So this has consequences, and it has metaphysical consequences as well. I think many of you will already see where I'm going here. The probability space is the space of possibilities, right? That the probability function defines. So I want to come to this today. That's the lesson for today. But let me just make sure that you don't misunderstand the proposal. I'm not saying propensities generate probability functions. You may think, oh, well, that he's saying there are some fundamental properties are dispositional and they generate all these probabilities. And the explanatory story ends there with this fundamental dispositional properties. There are people in the literature who claim, who ask the question, where do those dispositional properties come from then? And you may think, oh, well, he has no answer to that question because he's assuming as a primitive. Well, I'm not actually assuming anything as a primitive. You could have what people call nested dispositions all the way down. This is a phrase that Hugh Mellor used to employ. Dispositions all the way down means you never find the fundamental properties or the fundamental categorical properties. They're all sort of underpinned by further properties. And there's a never-ending point in that explanatory relation. And I have nothing against that, and nothing in what I say, nothing in this proposal militates against this idea. It could be that there are propensities all the way down, and there's never a final level of explanation that you reach. That's consistent with what I'm saying. I'm just saying any probability distribution that is objective and objectively measures chance must be underpinned by some propensity that generates it. But then that propensity may be the outcome in an outcome space of another probability function generated by yet another propensity, which in turn may be, and so on and on and on, and who knows where we end. And I don't know, there's a final ultimate end where reality stops, and that's the fundamental blocks of the universe, and everything is constructed on the basis of that. Maybe there is, but maybe there isn't. Nothing in what I say militates against either option. I'm just proposing a formal framework for understanding the relationship between propensities and probabilities, but the propensities themselves may be outcomes in outcome spaces of further probability functions defined or generated by further propensities and so on. Okay, so for instance, in the case of the coin, you could say, where does the fairness of the coin come from? And it may be that it comes from a machine, the machine that produces coins. I think in English, this is the mint, right? This is the mint, the Royal Mint of England, I think, not Britain, of England, is the one that produces the pound sterling coins. Well, maybe there are properties in that machine, in the mint, that generate this coin, that explain why some coins are fair and why some coins are biased, right? So that's perfectly possible. And so it may be that the propensity of being fair or being biased of a coin, of a pound coin in this particular case, is further explained by some propensities of the machine that produced them. I have nothing against that, and nothing in what I say really militates against that. So the propensities themselves could appear as part of the outcome spaces of all the probability functions, but they cannot appear in the outcome spaces of the probability functions that they themselves generate. That's the only point I'm making. Okay. Okay, so come to this toss, and I told you I'm going to try to show you today. I'm going to try to disabuse you today and convince you that what you thought was really simple is actually, this is what philosophy is for. Philosophy is, you come with this idea that something is really simple, and you leave the philosophy class realizing it's a lot more harder and more complex than you thought. So that's what I'm doing today. So you think, tossing a coin, very simple. It's symmetrical. It looks pretty geometrically even. You can roughly estimate that it probably weighs the same on one half and the other half. So probability half. Why? Because of a principle of indifference. I have no reasons to suppose that one half is heavier than another. And so that's why we give the probability one half to tails and heads in a coin toss. No, wrong. You thought that's not the reason why a coin has a probability of falling heads being one half if the coin is fair. It really does have very little to do with the makeup of the coin, other than the fact that the gravity, the center of gravity of the coin, and that's a dynamical concept, gravity is the same as the geometrical center of the coin. The details of the coin could be whatever. And you could even have coins that are loaded heavily on one side. But if the center is approximately the geometric center, the center of gravity, in the dynamical motion of the coin, then it continues to be fair. The coin continues to be fair. The way of making a coin unfair or biasing it is not by loading it on one side, but by bending it. Because then you make sure the center of gravity doesn't agree with the geometrical center. And that's what will produce different probabilities for heads and tails. And how do we know that? Well, we have to describe the dynamics of the coin toss. Just looking at the coin sitting, just looking at the euro coin sitting on this is not going to appear on film, but I can tell the people who are watching us on Zoom that I have a euro coin and it's on the table. Just looking at it really hard and studying it as hard as you can while it's there sitting, it's not going to tell you anything about what the probability is of it landing heads or tails. You actually have to study it in motion. You have to put it in motion and create a dynamical model for it as it moves. And that's what's going to give you the information that if the coin is fair, the probability of heads is one half. Well, somebody did this in 1986, no earlier. You may have thought, Laplace, surely at the beginning of the 19th century, the coin, come on. No, nobody thought of doing this before Keller in 1986, but he did it. He created a dynamical model for the coin toss and he studied it. He studied it in motion. He studied what the motion of the coin would be in the air, how it would rotate, and given the initial conditions and the distribution of possibilities in the initial conditions, what the likely probability would be for it to fall heads or tails. And it turns out that the coin is a special, the coin toss, the coin in the air is a special dynamical system to which all the method of arbitrary functions discovered by Poincaré and others applies fully. which has the lucky feature that if you have a very slight uncertainty over the initial conditions, a slight uncertainty over the push, the upwards velocity and the angular velocity of the coin, then the only thing you can say about the coin and where it will land and whether it will land heads or tails is that it has a probability 1/2 of landing heads or tails. And that probability is robust over the uncertainty over the initial conditions. Very few systems have this property. Well, actually, quite a number of systems do, but not all systems by any means have this property. But it turns out that the coin in the air does. And that's where the probability 1/2 comes from. Now, to describe this dynamical model, like in any model, you have to make a number of idealizations. You idealize your system. Every scientific model idealizes the system that it treats. And so Keller assumed that the radius of the coin was A, and it was a perfectly spherical coin with no protuberance of any sort. That the coin's thickness, look at this idealization, the coin's thickness is negligible. Why is this important? Because if the coin has some thickness and there's a finite, maybe a small, but non-zero probability that it may fall on the edge, you cannot rule it out. And that's going to screw up your 1/2 probability ascription. So you have to assume that it has no thickness. So it cannot possibly fall on the edge. The coin center of gravity is its geometrical center. This is a key assumption. It's true for every system that exhibits. This, the coin is initially at height A from the surface. You're tossing it from just there, just below here. Then you toss it very high with a certain upward velocity, and then it falls and it doesn't rebound. Just falls like flat, no rebound. Okay, it's like it falls on sand, but actually it doesn't fall on sand. It falls on a really hard surface that behaves like sand. It's a model, you know, you're entitled to do these things. And finally, the coin's angular velocity remains constant throughout. That's a pretty major idealization when you start thinking about it, because there's air, there's friction, but we're just going to assume none of that has any effect whatsoever on the system. With all these assumptions in place, tossing the coin from the beginning from this position on, you can show conclusively that if the only three parameters this comes out of the idealizations are upwards velocity and angular velocity of the coin, and you obeys all these idealizations, then you can show that even if the underlying dynamics is deterministic, it's a Newtonian system. It's a classical mechanical system. Any uncertainty over the initial conditions, and there's always uncertainty, you're going to be infinitely precise with the upwards velocity and the angular momentum. Any small uncertainty will give you a 1/2 probability distribution over the final outcome, heads or tails. And this comes out of this method of arbitrary functions that started in the tradition of Henry Poincaré and others, but nobody had thought of applying it to the coin toss before Keller did that in '86. So this does not depend on the symmetry of the coin, and it's completely independent of any principle of indifference regarding the physical features of the coin in itself. You really have to put it in motion and imagine it as it moves in order to get this result. And what you get is that for the initial distribution of angular momentum and upwards velocity, you get this kind of array in which this first section is heads up, that second is tails up, that's heads up, that's tails up, that's heads up, and any distribution of uncertainty over the initial conditions is going to give you a 1/2 probability distribution over heads and tails, because if you add up the regions where it's heads up, that's exactly half of the phase space, the outcome space for this phenomenon, and tails up is exactly the other half. So that's what determines that the probability is 1/2. So the simplest example that you can think of already exhibits a lot of complexity, and it's already telling you lots of interesting things. And I claim what it tells you is that you need the tripartite conception. You need to distinguish these three notions. First of all, there are the properties, the physical properties of the coin, whether it's a perfect circle, how much it weighs, whether it's slightly bent, how thick or thin the coin is. All these features of the coin are important. They are the propensities because they partly determine the probability distribution. If there were significant differences there, the model would no longer apply because the idealizations would not apply, and you could no longer prove that the probability would be 1/2 for heads, 1/2 for tails. So first of all, there are the properties of the coin, the physical properties of the coin. I call this the propensities. Then there's the probability 1/2 heads, 1/2 tails, which is the outcome of modeling a dynamical process that takes place with this object in a particular setup, in a particular given context. And the closer you can get to the idealizing conditions, the better the model is, the more secure you can be in the conclusion of the single case chance or probability. But in any case, a single case chance of probability is a feature of a dynamical process, the dynamical toss. It's not a feature of the coin itself. It makes no sense to ascribe to the coin in itself any probability. Only when you do something with it, you get a kind of phenomenon that you can describe probabilistically. And finally, of course, I already told you, you can run the experiment with a coin in the conditions in which you are and collect the frequency statistics for it. So you need the tripartite distinctions here to make sense of Keller's treatment of the dynamical toss of the coin. You need to distinguish the propensities, the underlying physical features of the coin that give rise to the single case chances or probabilities in a dynamical process in which the coin is playing a central role. And then you can collect the statistics which may agree better or worse with the predictions of the model. If the idealizations are way off the mark with respect to your toss, if you're making the experiment with a coin that's really thick, then your test is probably not going to give you 50-50. But that's because the model doesn't apply there. Okay, but you collect the statistics precisely in order to test how good the model is for the situation at hand. So I claim you need the three distinctions. The propensities partly explain because they generate the single case chances, but they do so in the context of a dynamical phenomenon, not just by looking at the object itself. You cannot really just get that by looking at the object. So a coin's propensity, which is the features of the coin in itself, cannot explain why a particular coin lands heads on a particular toss, and it cannot therefore be refuted by a single toss of the coin. Single toss of the coin giving you heads is compatible with lots of different arrays of coins with very many different kind of properties in very many different types of tosses. So the single experimental outcome cannot refute the probabilistic ascription. This is, of course, something that Popper knew very well, and it was giving him headaches because what it means is that you cannot use hypothetical deductivism to test a statistical theory. It does, however, the coin's propensity does, however, specify the possible outcomes. It's in virtue of the coin having the properties that it does in the context of it being tossed that you can tell that the outcomes are just heads and tails. If the coin is much thicker, then you will have to introduce heads, intermediate, tails, because that would be another possible option and it should figure in the outcome space. So it's something about the propensities that settles the probability space, the space of outcomes over which the probability function is defined. And finally, the model as a whole is what explains the long run frequencies of outcomes. So Keller explains why a fair coin that has the appropriate propensities tossed in a particular given way should give you 50-50 in the long run. And when you run the experiment, you can explain the results of that experiment by appealing to the properties that are ascribed to the coin in the context by the model. It's the model, the Keller model, that's doing the explanation. And the Keller model appeals to the propensities, but it appeals to more. You cannot just rest with the propensities in themselves to get the full explanation of the statistical phenomenon. By the way, that's something else that I picked out by in a very large measure from Paul Humphreys. He was very keen that statistical explanation was this complex affair with all these different elements. Okay, the new lesson that was not that I didn't know last year. This is a new thought that has occurred to me since, but it comes out very naturally of all the stuff that I presented last year. Is that the propensities in the end, what they do is they generate the sample space. As I said, they generate the space of outcomes. They're the ones that determine whether you can have heads, tails, something else, what's in the outcome space of the probability function that gets generated when you toss it. But if you think about it, what this means is that the propensities have a particular relationship to the modality of possibility that is involved in probability ascriptions. Because when you describe a probability, you describe a space of possible outcomes, and that determines the possibility space for that particular experiment. So the propensities are here, they're limiting and quantifying what I would call the domain or the realm of the possible in that experiment. They tell you what the possible outcomes are. And then when you construct the appropriate model for the dynamical process with that system, you even get the probability functions. That is, you get to quantify the possibilities. For instance, in a biased coin, maybe heads is more likely than tails. Well, and I can tell you exactly how much more likely if I run the dynamical model for it. Maybe heads is twice more likely than tails. So the probability for tails is 2/3 and the probability for heads is 1/3. That's a very strong formal quantification of possibilities. You're quantifying possibilities when you provide a probability description. And what I'm claiming is in the case of objective probabilities, this is something that propensities will allow you to do. They generate the probability function, therefore they generate the space, and then they generate the numbers that quantify over the elements in that space. So nowadays, and I don't think this was there last year, or maybe I was beginning to think about this last year, but nowadays I want to think of propensities as a rather abstract designator. I no longer think of propensities as something very specifically in the object. It's rather whatever properties of the object determine the probability space and quantify over that probability space in a Chauncey experiment. I'm going to just from now on, well, from a few months, from the end of last year, begin to talk of propensities in this way. And this is very helpful because, as you know, metaphysicians can really agree on what propensities, what the damn things are. And there's a big disagreement. So I don't actually have to tell you what propensities are. They're whatever goes on in the system that fixes the probabilities, the objective probabilities of 1/2 heads and 1/2 tails. That suits me. And whether that's tropes or universals or indeterministic laws or what is it, I don't know. But I don't know what it is, and I'm frankly, I'm not that interested either. What interests me is that we know some systems that generate probabilities with certain regularities, and I'm just going to deal with those systems and treat whatever features those systems have that generate those regularities as propensities. So this is my new theory of propensities. I'm not sure this is where Paul wanted to go. But I think he's partly responsible for having taken me here. So a fair coin is fair. It has a propensity of being fair in that whatever configuration of a coin's features is capable of yielding this 50-50 single case chance in a particular type of toss within the context of its experimental trial. That's it. That's the propensities of the coin. Are they down to atoms and molecules and how they're configuring the coin? I really don't know. And I don't know that we should care too much about that. I care about what the system does when you do experiments with it and how best to describe it in a model. Okay, so what this means is the properties may change a lot and we don't really know what's going on at this fundamental level, ontological level. But there are some systems about which we know a lot about its behavior when we do certain things with them. And that may not capture the same parts or mechanisms in every case, but I claim it captures the same propensities. There's a pretty abstract designator, propensities for me nowadays. It designates very generally what causes these single case chances or probabilities. Okay, I said this is interesting because it connects us with modality. There's a huge literature on modality, and I just need 5 minutes, but I would like to say this because purpose of today's talk, really. Philosophers, metaphysicians have been distinguished into kinds of possibilities. In the recent literature, there's quite a lot of debate about this. They're objective and epistemic possibilities. For instance, Till, Grunewaldh, and Evas, Joly, and Verlaine have been writing some really nice papers on this, and they make some really tight distinctions. And I'm pretty convinced by this. It's conceptually sound to distinguish these two types of possibility. Timothy Williamson has done it too, but in his own more formalistic and more philosophy of language sort of oriented way. He also appeals to a similar distinction. So clearly, what I'm saying here is objective nomic probabilities, which is what I'm talking about, clearly will quantify, what they're quantifying is objective possibilities. That seems to make sense, and I don't see any reason to deny that. So when you toss the coin, these objective probabilities, they are objective because they quantify and delimit objective possibilities. It is objectively possible that the coin will fall heads, and it's objectively possible that it will fall tails. And it's the model appealing to the propensities of the coin that delimits those possibilities and quantifies over them. And so I'm quite happy to think these are nomic objective possibilities, as Eva and Till would say. Then presumably there'll be subjective probabilities that quantify over the epistemic possibilities. And remember, I started this talk by distinguishing objective and subjective. So I have no problem at all with this. I think the prima facie sound thought, and unless you give me an argument to the contrary, I continue to think this, is that propensities quantify and delimit objective nomic possibilities, which are the ones that appear in probability spaces. And that's what science studies by its empirical means and methods. But of course, this is not to deny that we have beliefs about those propensities, and we can have better or worse beliefs about those propensities. And in fact, people in the field have run Bayesian analysis of modeling, in which different agents will have different degrees of confidence in different models for a phenomenon. And those probabilities are clearly epistemic, and they're ranging over epistemic possibilities or degrees of belief in the mind. If you think the Keller model applies to your system, if you're convinced, you have a strong epistemic degree or degree of belief in the epistemic possibility that the model is right. Well, that's epistemically quantifying over the propensities with objectively quantify over the objective possibilities. Yeah, so what? I mean, we do this all the time. We have epistemic approaches to the kind of knowledge that we have about objective matters of fact. So the only difference is that here, the objective matters of fact include themselves probabilities. So you have degrees of belief, which are measured by subjective probabilities about models that you have and how appropriate they are for some objective probabilities. How do you then figure out what your overall probability estimate is for the coin to fall heads or tails? Well, I don't see any reason why a multiplication rule wouldn't work here. If your degree of belief in the Keller model is 60%, and the Keller model says the chance of heads is 50%, then your degree of belief that it will fall heads is 60 times 50. Why not? 0.3, that's your degree of belief. So in principle, this seems to get you around the problem of nested models and the problem of uncertainties in the models, which is clearly a problem, I don't deny. The Keller model is just a model, and it may be better or worse for different cases. Although it's not automatic, and here I was troubled by something that I found in Paul's writings. I've been reading a lot of Paul since he died. I also read a lot of Paul before he died. Specific probabilistic models, he says, are needed to apply abstract theory to real systems. And I think he's right here. Kolmogorov's mathematical theory is just a schema. Those axioms are just a schema. They describe a formal concept, the probability concept. But how to apply the concept to the real world is dependent on a physical model of the situation. And that's what the Keller is doing. It's giving you a physical model to apply this formal abstract mathematical concept, Kolmogorov probability, to the actual physical system of tossing the coin. You need the intermediate. You cannot get to apply probability theory straight on the system without the model. I think he was just full of good ideas, and And as you can see, I'm in a way just working out the details of things he said in the past. Okay, I don't want to bore you with this, but I've actually put this to good use in solving problems in the foundations of science. I said I solved the measurement problem. Believe me, I mean, nobody believes me, but everybody has this poor, low epistemic estimate in my claim that you can solve the measurement problem by using propensities in the way that I've just described them here. And even before I had this whole theory of propensities, the tripartite conception and so on, I already knew the measurement problem could be solved, and I did solve it in a British Journal for the Philosophy of Science paper many years ago. And if you look at the details, I won't discuss them here, you have them on the slide. But it's just basically an application of this tripartite conception and this Humphreys idea that you need an intermediate physical model to apply probability theory to the concrete physical world. You can't do it without an idealizing model. And so what quantum mechanics gives you is an idealized model of quantum measurements. And if you employ it properly, you can get the right probabilities out without incurring contradictions. I still believe this. And this solves the measurement problem. I don't know why people don't, I mean, it's obvious to me. But, I've done the same thing more recently with fitness, and I think I've talked to some of you about this here, but basically the paper on the complex nexus of fitness just follows the same strategy. I applied the tripartite conception and distinguished three different things that fitness really refers to. It refers to the propensities, are the properties of the organisms. It refers to the single case chances that those organisms reproduce, and therefore, from a genetic point of view, pass on their genes. And it refers to the actual population statistics that we run on reproducing success for any given organism in a particular biological context or a particular environment. And people have been quarreling about what fitness really is. And I claim, well, fitness is actually all of it. You're right, fitness is organismic properties, and they can be ascribed at the individual level. But you're also right, fitness is a statistical property of the population, yes. And you're also right, fitness is what you measure in the laboratory, yes. It's all of these things together. And why? Well, because it's an objective probability. It's measuring an objective probability, and objective probability has at least three parts. So fitness necessarily must refer to those three parts. And if you do that, then I claim some of the problems in the philosophy of biology relating to fitness can also be solved in the same way. I know it's ambitious, and I don't understand why I have so few followers here, but I think you can solve these problems by means of this theory. So it's actually not just philosophical abstract theory, but you can put it to use in the foundations of scientific disciplines, and you can put it to good use I would call it good therapeutic use, because a lot of these problems are just Wittgensteinian problems of misapplication of relevant categories. And when you distinguish properly the terms that appear in your vocabulary, the problem just goes away, as Wittgenstein brought back to life in probability. Conclusions. So I nowadays claim propensities are abstract descriptors for the properties of systems that yield stable probabilities. And I don't know what the underlying properties of the systems are that explain that. And I'm not sure that we're ever going to find a unique or universal recipe to find out those properties. I'm more interested in what the systems do in practice, and that's what I call propensities. What they do mainly is to delimit objective nomic possibilities for you. They tell you what the options are, and they tell you how likely the options are. And that's subjectively the objective options that there are. And science is informing you as best as it can about these objective options. Their theoretical description typically yields some rule or procedure to mathematically represent those single case probabilities. You see it in the Keller case. You get the probabilities when you run the model with the appropriate idealizations, and it's a very robust result. It's a mathematically robust result. And they can be tested experimentally by frequency ratios in the way we test any claim. admittedly, you have to run a lot of tests when you're running a statistical experiment. You're never going to refute a theory by means of one experiment. That's in the nature of statistics. But you can test things in statistics too. And finally, the careful application of this tripartite conception of probability is philosophically really useful. I continue to think this, believe me, in solving some of our philosophical disputes and diseases and illnesses by this really good medicine. And if you apply properly, you can solve these problems. And I claim to have done it in 2 cases, which are recalcitrant problems in 2 different fields in philosophy. But I'm not going to end there. Now I'm doing the same thing with chemistry, reactivity with a colleague. We have a paper coming up, applying the same framework to understand the notion of reactivity. And it works and it solves some problems. I claim, but this is work to do in the future. You can also apply it in observational astrophysics, ecology, and different areas where statistics is used routinely to get stable probabilities. In all those cases, I claim, if you have this tripartite conception, it helps. It helps you as a philosopher, at least. You feel better in yourself when you have this tripartite conception. Obrigado. That's all.